Let me just see if I can grab that quarter right there. It's not there. What's going on? It's actually at the bottom of this contraption. There it is. This is a special case of your elliptic paraboloid, where the semi-axes of the ellipse are the same, so it's actually a circular paraboloid, more commonly known as a parabolic dish. Right? You see them in flashlights, for instance, and telescopes, and solar collectors, and lots of other things. Here's how it works. If you have a quarter on the bottom of your dish here, and this is actually a parabolic cross-section. Remember, a parabola takes light near the focus, or at the focus, and bounces it off using angle of incidence equals angle of reflection into straight parallel rays, right? It's the reverse of it's how the flashlight works, right? The flashlight has a filament here, and it bounces off the back parabolic dish, and makes a long beam that sends parallel light rays out. A solar collector collects it and focuses it here. These big radio antennas may have a parabolic dish and focus light to a point like that. It's a very important property of parabolas. But when this bounces off and straightens it out, this new parabola has a focus up here, and each point on here, the light is refocused to a point up here. It creates a false image of your quarter at the bottom. So there's a common optical illusion. And we're going to return to that today. The main topic for today, actually, is Stokes Theorem. Oops. Put this down. Stokes Theorem says this. Suppose sigma is an oriented, smooth surface in x, y, z space. Enlarge this a bit. So an oriented, smooth surface in XYZ space bounded by a simple closed smooth curve C with positive orientation. And let f of XYZ be a vector field. So here's a vector field, maybe it's the velocity field for a fluid flowing through here. And you want to calculate the circulation, which is this line integral, f dot dr along the boundary. What's the circulation around the boundary? This is also how we define work in physics, right? We can calculate this circulation around the boundary by taking the flux of the curl of f, the velocity field that goes through here. And it doesn't matter actually what the surface is. If this is the boundary, it's a nice smooth surface. You can take a small surface here, a great big surface here. It all gives the same result, and it's equal to the circulation, the vector line integral of f along the boundary. That's Stokes theorem. There's a nice Wikipedia write-up. Maybe I should put it up here just briefly. There it is. So here's the boundary of a surface sigma with normals oriented so that you move around counterclockwise. If these are upward normals, for instance, they call that positive orientation. This is the f dot dr written in its other format, right? In 3 dimensions, p dx plus q dy plus r dz, where f is the vector with components p, q, r, functions of x, y, and z, is equal to this. And this is just the curl of f dot n ds over the surface sigma. You have a nice write-up here in Wikipedia you can look up. So it's useful in governing viscous drag in fluids. You can go click on Stokes' law and so forth and look up some interesting applications of this. Well, for us, we're interested in the mathematics of this. Let's look at it as an example here. Suppose we wanted to apply Stokes' theorem to evaluate integral along the closed curve, C. You can put a little circle on here if you want, with f equals I plus 2x minus x squared, I plus 2xj minus x squared plus y squared k. And suppose we're interested in calculating this line integral around the unit circle in the xy plane that bounds the unit disk x squared plus y squared less than or equal to 1. If we orient our normals upwards, let's apply Stokes Theorem. Integral f dot dr is equal to the double integral over the surface, the disk here, curl f dot n ds. Right? Well, what's the curl of f? We put f, 1, 2x minus x squared minus y squared, into this determinant with I, j, k, and ddx, ddy, ddz. To calculate the curl, we get minus 2y plus 2x, 2. And so there's curl of f dot n. The unit normal, since it's supposed to be perpendicular to the surface, it must be 0, 0, 1. We don't even have to calculate it. And so minus 2x times 0 plus, minus 2y times 0 plus 2x times 0 plus 2 gives us the integrand of 2. We'll double integrate 2 over the surface. Well, pull the 2 out. This is just twice the double integral over the surface, which you recall is the surface area, right? If you integrate 1 ds, you get the surface area. So this is twice the surface area. The area of a unit disk is pi times 1 squared, right? Pi r squared is pi, so we have 2 pi is the work around this closed curve. Too bad it wasn't a conservative field, right? We just immediately say, wait a minute, the integral around a closed path is 0 would be done without a calculation. Oh well. This is what Stokes Theorem is for, is when you don't have a conservative field, right? Otherwise you get 0. Now, one of the points was that you can do this in 3 dimensions, right? You don't have to have a flat lamina, you can have a curved lamina. Suppose we take the same unit circle, but now we bound it with this surface. We're going to come up with exactly the same value for the line integral using this surface as we did for the flat disk in the xy plane. This might be our circular paraboloid, for instance, right? Maybe it's got the equation z equals 1/2 times 1 minus x squared minus y squared. It's off the end of the paper there. In that case, remember our f was 1, 2x minus x squared minus y squared. And we take the curl of f, we got minus 2y, 2x, 2. So it's the same curl of f because it's the same field, it's the same curve, we just changed the surface. Now unit upward normals to this new surface are, well, rather than compute unit normals, I'll do this instead. I'll say that Stokes Theorem says line integral f dot dr is surface integral curl f dot n ds, this time over this surface. And the surface integral theorem said that we actually don't have to calculate this unit normal. We proved that you could rewrite this as integral curl f dot n dA over the region A, the region that's R, that's the projection of this surface, which is our unit disk we had last time. So by our surface integral theorem, this integral is equal to curl f dot n, where n is minus dz dx minus dz dy1, upward normals, dA. And so now we get minus 2y, 2x2, dot product with minus x minus y1 is what this normal comes out to be. When you take the derivative of 1/2 minus 1/2 x squared minus 1/2 y squared, there's the normal. And once again, we get double integral of 2 dA over the region that's the projection, again the surface. We get the same thing as before, 2 pi. What we really did before in the last example, if you think about it, was apply Green's theorem because it was a plane region. Now it is true that f here has a third component, but it fell out in the washer when we took the dot product, it went away. So effectively we're just applying Green's theorem in the last example. Now we show that Green's theorem extends to curved surfaces that have a boundary curve, and this curve doesn't even have to be in the plane. There it is, Stokes Theorem, what I consider the crowning glory of calculus because end of calculus, because it pulls together all the things about line integrals and surface integrals, multiple integrals, and vectors all into one theorem.